This robot has been designed over the last 2 years by about 15 seniors in the Department of Mechanical Engineering at Colorado State University to go into collapsed or partially collapsed buildings and try and find people who might be trapped there in the event of a disaster. The major components of this robot are the differentially skewed tracks, which means that we can have a zero turning radius and also go over very rough obstacles. With the macro scale tracks, it also allows us to climb stairs and obstacles that are almost as tall as the robot. We have 2 drive motors that drive each of the tracks here, as well as an articulation motor underneath here that allows the robot to change its geometry, which you'll see later. The robot control system is comprised of motor controllers. Those are run off of a carrier board, which handles all of the communications routing within the robot, sends the signals to the motor control boards, which have their own microcontrollers, and also has microcontrollers to control the pan tilt of the camera system. So each of the drive motors is actually controlled by one of the motor controller cards here on the motor control bus. Each of these motor control cards is a closed loop system. It uses a pulse width modulated signal and an H-bridge to give us bidirectional speed control for each of the motors. The third motor control card is actually for the articulation motor, which is buried under here, and which allows the robot to change its shape, as you'll see later. Each of the motor control cards has its own microcontroller, which is fed information about what it should do by the carrier board, which is over here. Now, the carrier board fundamentally handles all of the communication routing on the robot, and it also takes care of most of the power distribution. The carrier board also controls the pan tilt mechanism for our cameras. The carrier board actually gets its information from what we call a relay server, which is a Java-based web server that sits on the robot, and it allows us to communicate through our wireless router here. The camera relay server also handles all of the camera signals, which are just standard analog video feeds. So we have 2 cameras on the robot, both of which are able to display images on the laptop, which is running a graphical user interface for remote control of the robot. This is what we call a zero lux camera. It has the ability to see in complete darkness because it's sensitive into the near infrared. And this is actually a thermal imager which can read the surface temperature of distant objects. Well, the Good Samaritan actually runs on 3 different battery packs right now. This is just a lithium-ion battery pack. It's fairly high capacity and pretty low voltage and just runs our router. This is another lithium-ion battery pack and runs all of our boards and the camera server and some of that kind of stuff. And these are the drive batteries, and these are the ones that are really worth mentioning because these are lithium polymer batteries, which means that these have about 8 times the capacity, 4 times the voltage of this battery pack, for example, and yet they weigh about exactly the same. And you can see that they take up not very much more space either. The downside is that while this battery pack we were able to buy the components and make ourselves for about $12, this battery pack costs about $350. When all 3 of the motors on this robot are operating at full torque and are near stalling, we actually have a 40 amp power drop. And so one of the reasons why we have to go with lithium polymers is that they're really the only battery aside from lead acid that even has a chance of giving us 40 amps. So these are actually not even standard lithium polymers, these are special high current lithium polymers. By comparison, these are capable of outputting about 2 amps. The entire Good Samaritan robot is actually constructed of carbon fiber composites. This gives us one of our unique features, which is our extremely lightweight. This entire robot, with all of the batteries and motors and equipment that it carries, only weighs about 23 pounds, including 3 pounds of ballast to move the center of gravity. Also, buried within the carbon fiber composites, we have a tensioning mechanism which gives us a nonlinear spring force on our track. This means that we're far more resistant to detracking than most comparable robots. One of the aspects of this tensioning system is that it has to be pre-tensioned before the robot can be driven. So right now I'm going to show how that's done. We have an air port on the side sticking out of these uprights that allows us to plug a small air compressor in. And these are then pressurized through this port to over 200 psi. So now the robot's ready to drive. This is actually the control station for the Good Samaritan. It consists of any standard PC laptop, a video game controller, And there's a very good reason for that. When these robots actually go out into the field, they have to be used by rescue workers who have never driven the robot before. So we try to make this as video game-like as possible. If you can play a video game, you can probably drive our robot. And then also a wireless USB connection to move the data back and forth from the robot to the laptop. This is the graphical user interface. Primary aspects here are just a camera window, and we can view either the thermal imager or the zero light camera. Also an indication of what position our robot is in, and a timer to tell us how long we've been active. In order to start up the Good Samaritan, first part of the procedure is actually to plug in the router and wait for it to acquire a network signal. Then we have a boot mode and a run mode back here on this switch. So it's important to make sure that we're in the boot up mode. And as soon as we have a solid signal on the router, which we do now, then we can go ahead and start the robot, turning on both the controls power and the robot power. So now we have a flashing red LED indicating that we do have a network connection. And we can go ahead and switch into operational mode. So this GUI, which is written in LabVIEW, we just go ahead and start, and then we wait just a second for communication to be established, and we're able to start driving the robot using the controller. These two analog joysticks here provide the main motion control. Point of view hat moves the camera around. These buttons control what we call the articulation of the robot, so what angle the robot is sitting at. And we can also switch between the different camera views. So this is a very, very uncluttered, by comparison, example of what we might see in a real arena for this competition. We see a couple pallets and some cinder blocks and a simulated victim laying around, which we'll now kind of drive around and we'll see if we can find the victim. Alright, so as you can see, we've now lined up the human in our field of view with the camera, meaning that we were successful in finding it. And we can see it both on the visual spectrum, and also we can switch over here to the thermal mode, and we can see it much more clearly. Thus you can see part of the advantage of the thermal imaging system over a visual system. Other advantages include that it can see partially through walls, it can see under trapped piles of rubble, and it can also help us spot fires that might be in existence.